Last video, we saw how common functions could be rewritten as power series, and we even managed to do it ourselves for a number of examples. But so far, all of our examples relied on being able to somehow rewrite the function formula in a form that lined up with the geometric series sum formula, because that was the only method we had to convert between algebraic formulas and series. But, as you might have guessed, this method can only go so far, because there are functions, like e to the x, sine of x, and cosine of x, to name a few, that pretty plainly cannot be written in a form similar to 1 over 1 minus x, or at least it's certainly not obvious how. And yet, last video, I showed you the power series representations for several of these functions, so it clearly can be done, so how do we do it? Well, the truth is, the geometric sum method, while very clever, is kind of a hack. It works when it does, but it doesn't really get to the heart of the matter. What's really going on that allows us to get these power series representations at all? As I mentioned briefly last video, the idea is we build up the power series term by term with increasingly better polynomial approximations of higher and higher degree. We start with a linear approximation, then get a quadratic approximation, then a cubic approximation, and so on, and in the limit, we obtain the power series representation we're looking for. But, of course, what I did not mention last video was how to derive these successive approximations. We already know how to get a linear approximation. That's the same as finding the formula for a tangent line. But how do we get a quadratic approximation, or a cubic approximation, or a degree 314 approximation? Think again about how linear approximation, or tangent line approximation, works. Let's say we want to find the tangent line to this function at the point x equals 0. Every line is determined by two numbers, its y-intercept and its slope, which I will label as c0 and c1 in this case. The way we construct a tangent line is we make both the y-intercept and the slope agree with those of the target function at the point of tangency. That is, we want the value of the tangent line at x equals 0 to equal the value of the target function at x equals 0. L of 0 equals f of 0. But we also want the derivative of the tangent line to equal the derivative of the target function at x equals 0. So L prime of 0 equals f prime of 0. Writing out the expressions for L of 0 and L prime of 0 more explicitly, we find the coefficients c0 and c1 must be f of 0 and f prime of 0 respectively. Similarly, to obtain a quadratic approximation at x equals 0 for f, we need to determine three coefficients, c0, c1, and c2. We can determine what they are by requiring the quadratic approximation q of x to agree with the target function f of x at x equals 0, along with its derivative and second derivative. That is, we require q of 0 to equal f of 0, q prime of 0 to equal f prime of 0, and q double prime of 0 to equal f double prime of 0. Expanding these out, we get that c0 and c1 are, like before, equal to f of 0 and f prime of 0. But the third equation becomes 2c2 equals f double prime of 0, which means c2 must equal f double prime of 0 over 2. This pattern continues for a cubic approximation. We need to determine four coefficients, c0, c1, c2, and c3, but c0 through c2 are already determined from last time. We just need to determine c3. And we can get that by requiring that the third derivative of the cubic approximation at x equals 0 equals the third derivative of f at x equals 0. Or in other words, c triple prime of 0 equals f triple prime of 0. Doing so, we get 2 times 3 times c3 equals f triple prime of 0, which means c3 equals f triple prime of 0 divided by 2 times 3. And likewise, for a quartic approximation, we need to determine a fourth coefficient, c4, which comes from setting the fourth derivatives of the approximation and f equal to each other at x equals 0. This yields 2 times 3 times 4 times c4 equals the fourth derivative of f at 0, which means c4 is equal to the fourth derivative of f at 0 divided by 2 times 3 times 4. At this point, you might be seeing the pattern emerging. The nth coefficient c sub n of a polynomial approximation always obeys the equation n factorial times c sub n equals the nth derivative of f at 0. And solving for c sub n gives us the nth derivative of f at 0 over n factorial. Thus, in the limit, we obtain a general formula for the power series representation of any function. F of x equals sigma sum, from n equals 0 to infinity, of the nth derivative of f at 0 divided by n factorial times x to the power n, which, when written out term by term, is f of 0 plus f prime of 0x plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial times x cubed, and so on. This series is called a Taylor series. Basically, it means the same thing as power series representation. By the way, this notation where we have f with a superscripted n in parentheses is used to refer to the nth derivative of f. Basically, it tells you how many apostrophes you should attach to f if there are too many to write. All right, so let's finally answer the question that I'm sure is burning in all of your minds, which is, what is the power series expansion of e to the x, or in other words, the Maclaurin series expansion, or in other words, the Taylor series expansion of e to the x, centered at x equals 0. All right, so let's actually find that now. Okay, so according to what we just found, the Taylor series general formula, function f can be written out as sigma sum n equals 0 to infinity of the nth derivative evaluated at 0 divided by n factorial times x to the n. All right, so all we need to do then is we need to find out what the nth derivative for all of these values of n, the nth derivative of e to the x evaluated at 0. If we can find that for every possible n value, we will have our Taylor series. Well, all right. Before trying to jump into maybe the entire thing for an arbitrary n, let's start with some specific values. So where does the sigma sum start? It starts at n equals 0. So we'll start with the 0th derivative of f, which is, in other words, just the original function f. We haven't taken any derivatives. So what is f of 0? Well, f of 0, plug in 0 in for x, that is e to the 0, which is 1. Okay, so that tells us the initial term, or at least the initial coefficient, that is. All right, well, what about the next one? So f prime of 0, what's that going to be? Well, in order to get that, I'll need the derivative of f. So let me find that out. So f prime of x, take the derivative of e to the x. Well, it's just itself. So in that case, evaluate it at 0, and we're going to get, again, e to the 0, which is just 1. All right, so that tells us the first derivative at 0 is 1, as well as the initial coefficient. All right, so I think you can probably already guess what's going on, but let's just do one more, just to be absolutely sure. So f double prime of x, take the derivative of the derivative. It is, again, just going to be itself, evaluated at 0, and you get, again, e to the 0, which is 1. All right, so evidently, all of the derivatives of f evaluated at 0 are just going to be 1. All right, so that's pretty nice. All right, so let's go ahead and plug it in. So in that case, our Taylor series expansion is evidently going to be sigma sum n equals 0 to infinity of 1 over n factorial times x to the n. Or if I compactify that a little bit, x to the n over n factorial. All right, so we are done, at least with finding the series, although I think I'd like to write out a few terms of it anyway, just to get kind of a better sense of what this thing looks like, because it's still pretty amazing that we can even do this at all. So let's see what it really looks like. So if I write out the first few terms, I get e to the x. If I plug in n equals 0, then I'm going to have x to the 0, which is just 1, divided by 0 factorial. So this is something I hadn't mentioned before, but for reasons which I will not explain right now, 0 factorial is always defined to be 1. All right, so in that case, the 0th term of the series is going to be 1 divided by, well, 1. So it's just going to be 1. All right, what about n equals 1 then? Then I'm just going to have x divided by 1 factorial, and 1 factorial is just 1, so this is just going to be x divided by 1, or just x. All right, if I plug in n equals 2, then I'm going to get x squared divided by 2 factorial, which is just going to be 2. 2 times 1. And I'll do one more. I think I'll get x cubed divided by 3 factorial, which is 3 times 2 times 1, or in other words, 6. And we just keep on going from there. I guess I'll write down one more. X to the 4th divided by 4 factorial, which turns out to be 24. Just so you know where those numbers came from. All right, so very good. We have got our Taylor series, although before we get too excited, we should answer the second part of this question, which is what is its radius of convergence, which is important because this series is great and all, although it's going to be pretty pathetic if it turns out it only converges when x equals 0 and for no other values. If the radius of convergence is 0, this is a very lame series. So let's try to find what that is. So we'll use the usual trick that we have for power series, the ratio test. All right, so I'll go ahead and reproduce the formula down here. All right, so we've established that e to the x is equal to x to the n over n factorial for some values of n at least. All right, so according to the ratio test, what we need to do is we take the ratio of the n plus 1 term and divide it by the n term, put that in absolute value, take the limit as n goes to infinity, and see when we get a result that is less than 1. But we'll worry about the limit taking later. For now, let's just write out what this is. So a sub n, what I mean by a sub n is just the term. So x to the n divided by n factorial, that's my a sub n sequence, which turns into a series if I replace all the commas with plus signs. All right, so in that case, to write this out, a sub n plus 1, I just turn every n into an n plus 1, so that's x to the n plus 1 divided by n plus 1, and then divide by the original, which I will render by multiplying by the reciprocal instead, to make things look a little cleaner. Oops, I forgot my factorial. Sorry about that. All right, divide by the original. Okay, so we have this going on, and I think we can see some cancellation already. X to the n is going to cancel with all but one copy of x up in the numerator, so I will denote that by getting rid of the exponent there. And what about this leftover bit? So we'll have x times n factorial divided by n plus 1 factorial. So this also cancels. So remember, the trick we can do with that is to kind of expand out n plus 1 a little bit until we get an n factorial appearing. So n plus 1 factorial, that is n plus 1 times n, and then it would be n minus 1 times n minus 2 times n minus 3 all the way down. In other words, n factorial itself. N plus 1 factorial is n plus 1 times the next lower down factorial. And then we get the cancellation we were looking for. So this then turns into absolute value of x divided by n plus 1. All right, and at this stage, I think it's simplified enough that we can take a limit easily. So I take the limit as n goes to infinity, and remember, in the context of doing the ratio test and taking the limit as n goes to infinity, we treat x as if it's just a constant. So x does not vary according to n. N can go to infinity, and x is just some fixed number as far as the limit is concerned. So in that case, x is just some number, whatever it is, and we are letting n go to infinity. So the denominator is growing without bound, the numerator is constant. So this thing, no matter what x is going to go to 0 as n goes to infinity. All right, and what does that tell us then? So 0 is less than 1, strictly less than 1. And so in that case, by the ratio test, we have that this series converges, and it doesn't matter what x is. We get 0 for, you can plug in any number you want in for x and take the limit as n goes to infinity. You get 0, which is less than 1. So the ratio test says this converges for all x. So for all x, from minus infinity up to infinity, all of them work. So in that case, our radius is going to be infinity, which also means, if you're interested, that the interval of convergence, which I guess I'll call I, is going to be minus infinity to infinity. All right, so we actually got the best of all possible worlds then with e to the x. This Taylor series winds up equaling e to the x for any value of x you pick, whether it's 0, whether it's 1, whether it's a billion, whether it's pi over 2. This series will compute e to the x for you. So that's a Taylor series of e to the x. I say a Taylor series because, like with general power series, you can center a Taylor series about different points to obtain different series representations. If you remember, we derived this formula for the coefficients of a Taylor series by requiring the polynomial approximation and the target function and all their derivatives to agree with each other at x equals 0. But we can choose a different value of x to be the point of agreement. If you change that point of agreement to x equals a instead, the formula for the coefficients changes slightly, and the formula for the general Taylor series becomes f of x equals sigma sum of the nth derivative of f at a over n factorial times the quantity x minus a to the power n, which, when written out, looks like this. We call such a series a Taylor series centered at a, or at x equals a. However, a very common choice for the center point is x equals 0, which makes the formula the simplest. When a Taylor series is centered at x equals 0, the Taylor series is sometimes called a Maclaurin series. All right, so let's go ahead and move on to example 2 then, and see if we can find the Taylor series for this function, e to the 2x, centered at a non-zero center point this time, in this case x equals minus 4. All right, so I'm actually going to show 2 different ways you can find this series. One is kind of a more general purpose kind of way, and the other is a bit of a shortcut method. Each one has its own merits, but so I would recommend go ahead and pay attention to both of those, because in different situations you may find one or the other being better suited. But I'll start with the general purpose method. All right, so this is just going to be based on the generic formula for a Taylor series centered at some other center point A. So what was that again? So that formula was f of x can be written as sigma sum from n equals 0 to infinity of the nth derivative of f, but instead of being evaluated at 0, it's evaluated at a, the other center point, which in this case is minus 4, divided by n factorial, and then we multiply by x minus whatever that center point is. So minus 4 in this case, so x minus a negative 4, that turns into an x plus 4. All right, so we're going to tackle this pretty much the same way that we tackled finding the Maclaurin series for just the generic function e to the x. We're going to focus on trying to find a formula representation for this thing, the nth derivative of f evaluated at minus 4. If we can figure out how to write that in terms of n, then we'll have our Taylor series. All right, so like before, let's go and write out a few derivatives of f and see if we can piece together a pattern in order to write down a more general expression for the nth derivative of f at negative 4. All right, so I'll start with the 0th derivative of f, which is, in other words, just the original function f. Well, it's no secret what that is. That's e to the 2x. All right, so what is its first derivative going to be? So I take the derivative of this. It stays the same because it's an exponential, and the chain rule says I get an extra coefficient of 2 popping out. So I have 2 times e to the 2x. All right, that's the first derivative. Pretty straightforward. What about the second derivative? So I take the derivative of the derivative. So in that case, I'm just going to get another factor of 2 popping out. So I will write that out as 2 squared times e to the 2x. And as for the next derivative after that, the third derivative, we get another factor of 2 popping out. So I'll have 2 cubed times e to the 2x. And at this point, I think you can see what kind of pattern is going on. The fourth derivative is going to be 2 to the 4th times e to the 2x. All right, and I think you can see how we might write a general formula then for the nth derivative. It looks like whatever derivative order we're at determines the exponent, or determines which power of 2 we're looking at. If we're taking the second derivative, we have the second power of 2. We have a fourth derivative, we have the fourth power. So it looks to me then, following the pattern, that the nth derivative of f at x is going to be 2 to the n times e to the 2x. Which tells me then that at x equals -4, which is the only point we actually care about in this case, we're going to get 2 to the n times e to the -8, or to write it another way, 2 to the n divided by e to the 8. All right, so we've got it. So let's go ahead and plug it in. So what are we going to get then? So f of x is going to be sigma sum n equals 0 to infinity of 2 to the n divided by e to the 8, but then divided by n factorial. So I think I'll group them all together in the denominator. So I'll put e to the 8 first, and then times n factorial times x plus 4 to the power n. All right, very good. So what about the radius of convergence then? So what are we going to get in that case? So we can use the ratio test again to figure that out. So if I take the absolute value of a sub n plus 1 divided by a sub n, what is that going to be in this case? So we'll have absolute value of 2 to the n plus 1 divided by e to the 8 times n plus 1 factorial. Oh, I'm forgetting my x plus 4 to the n, so n plus 1, like that, and multiply by the reciprocal of the original. So that's going to be e to the 8th on top times n factorial divided by 2 to the n times x plus 4 to the n. All right, so simplifying this out, x plus 4 to the n cancels with all but 1 of x plus 4 to the n plus 1 up above. And same story with 2 to the n, cancels with all but 1 copy of 2 up above. And e to the 8 cancels with e to the 8. So it looks like all I'm going to be left with... Oh, actually, so there's a little bit more I can do. So I have n factorial up here and n plus 1 factorial down there. So in this case, this n factorial will actually cancel with all but the single factor of n plus 1 that this n plus 1 factorial encapsulates. So I can cancel out the n factorial with the, well, factorial piece of n plus 1. All right, so it looks like when all the dust settles, we're just going to have x plus 4 on top divided by n plus 1 on bottom in absolute values. And if I go and take n to infinity in this case, then it doesn't matter what value of x is. It could be gigantic, it could be tiny, it doesn't matter. If n grows without bounds, this will eventually shrink to 0. Which, according to the ratio test, gives us convergence for all x. So the radius of convergence is infinite. All right, so like I said, that is just one way you can do this. It's kind of the most general way you can find the Taylor series for something. Find a general expression for the nth derivative of f at your center point and plug that in. You get your series, and the ratio test tells you what your radius of convergence is. So that is a pretty general way to, pretty much always works, but it does involve a bit of work. You have to go and take a lot of derivatives and see if you can find a pattern, and a pattern is not always obvious in these things. So it has its own limitations, but there is another way you can do this, which sometimes is a bit easier, which I'll go and show you guys now. So, alternate method. All right, so again, reminder. The task is to find a way to write e to the 2x as a Taylor series centered at x equals -4. All right, so the idea with this shortcut is we recognize that e to the 2x looks awfully familiar. It looks an awful lot like just plain old e to the x. And we remember that we already have a series representation for e to the x. It is sigma sum n equals 0 to infinity of x to the n over n factorial. And so kind of like what we did with the geometric sum formula stuff before we had an actual formula to find a general Taylor series, we can go and try to piggyback on this series expansion that we already have for e to the x. Well, one thing I can do already is, again, similar to the geometric sum formula, this equation, e to the x equals this series, holds not just for privileged values of x, but it holds for all x. So one of the things I can do is plug in e to the 2x in for x. In that case, I get e to the 2x is equal to sigma sum of 2x, quantity to the power n, divided by n factorial, which if I... Actually, no, let me not expand that out, so I'm not done yet. All right, so that's fine. This is actually a way to get the Maclaurin expansion for e to the 2x, but this is not actually what we were after, because we're wanting to get a Taylor series centered at x equals -4. And right now, if I was to go and complete this, this would give me a Taylor series centered at x equals 0. So I would have a Taylor series centered at x equals 0, which is cool, but it's not what we're really after in this case. So the question then is, well, is there some way that I can use this formula, which is already ready-made? It's already here. I don't have to go and verify it, and I already know its convergence properties and everything. Is there any way that I can convert this Taylor series centered at x equals 0 into one centered at where I want it to be centered at x equals -4? So if you feel like it, and I hope you do feel like it, go ahead and pause the video and see if you can think of a way you can kind of you can do that. So how can you go and convert this expression so that it has x -4 instead of just x showing up in there? Or actually, I guess it should be x plus 4. So I think I said x -4, x plus 4, because it's always x minus a. My bad. All right, well, one way to do it is to make use of the mathematician's standard trick, which is if you want something, if something doesn't look the way that you want it to look, then by golly, make it look the way that you want it to look. So what I'm going to do here is I'm going to plug in something in for x. I already did that once to turn this into 2x, but there's no reason that I can't do it again. So what I'm going to do is, well, I don't want x. I would rather have x be x plus 4. I would rather have x plus 4s showing up in my series expansion instead of just plain vanilla x. So, all right, by golly, I'll make it show up by plugging it in for x. Okay, so I plug in x plus 4 in for x, and then the series expansion becomes 2 times quantity x plus 4, all of that to the n power divided by n factorial. And this looks quite a bit more promising. If I go and simplify it out, I'm going to get, I think, 2 to the n divided by n factorial times x plus 4 to the n. And that is a power series that is centered at x equals -4. So we're good to go there. Although, as you might have noticed, I'm kind of cheating a little bit because this series definitely satisfies this condition. It's centered at x equals -4, And this equation is valid. It equals e to the 2 times x plus 4. But this is a different function than the one that I started with. I changed the function. So this is a series expansion for this function, e to the 2 times x plus 4, but it's not for the one that I originally wanted. However, with a little bit of algebra trickery, I can go and convert this function into one that contains e to the 2x and then solve for it. So if I go and simplify this out, distribute it through, I'm going to get e to the power of 2x plus 8. And using one of the standard exponent rules, I can break apart a sum in the exponent into a product of powers. So e to the 2x times e to the 8. And aha, that's the function that I originally cared about. And so what do I have? I have that this entire expression is equal to this series. So maybe I'll copy it down real quick just to make it completely clear what's going on here. All right, so e to the 2x times e to the 8th is equal to this series representation, which is centered where I want it to be centered, at x equals minus 4. So the only thing left to do is just divide both sides by e to the 8. So I get e to the 2x is equal to, and I'll put it inside the sigma in this case, sigma sum of 2 to the n divided by e to the 8 times n factorial times x plus 4 to the power n. Which, if I'm not completely mistaken, is what we had before. All right, nice. Well, or at least almost nice. So what about part 2 of the question? We are always forgetting about part 2, aren't we? What about the radius of convergence? We know it's infinite from the first method of doing it. And we could actually do the same thing here. We could go and do the ratio test here if we wanted to. It's not that difficult as far as it goes. However, you can actually get the radius of convergence also by doing this kind of piggyback trick. All right, so remember, the original series we started with was, or the original equation we started with, the original series representation that we started with was this one, e to the x equals this sigma sum. And we had that this series converges and equals e to the x for all values of x. So for all values of x between negative infinity and infinity. So what did I do in order to get the actual series representation that I got at the end? Well, I plugged in two different things in for x. I first plugged in 2x in for x, which changes the condition into minus infinity is less than 2x is less than infinity. And then I swapped out x for x plus 4. And so what that does is that will go and, where should I write it? I guess I'll write it over here on the left. That'll change the convergence condition into minus infinity is less than 2 times x plus 4 is less than infinity. All right, so what that tells us then is this series representation is guaranteed to be good for all x values that make this inequality true. And it sounds like I'm saying something rather complicated, but of course I'm really saying pretty much nothing, because if you think about it, all values of x, if you plug it in, no matter what value of x you plug into this expression, you're going to get something finite. You're going to get something greater than minus infinity, and you're going to get something less than positive infinity. So the convergence condition changed, but it just put on disguise. It's basically the same exact convergence condition we had before. So indeed, this expression is going to converge for all x, because this condition is always satisfied for all x values that you pick. So indeed, the radius of convergence is infinite. All right, so that's the shortcut method for you guys. All right, so let's go ahead and go on to example 3 then. So example 3. So this one is kind of more of an exercise of the general method that I used for example 2, except in this case the problem is actually going to give us a head start.
So example 3, the question is, let's suppose that for some function f of x, what am I trying to say? So suppose that for, grammar, come on. Suppose that for f of x, we have, by magic, the knowledge that the nth derivative of f evaluated at 2 is 2 to the n times n plus 3 times n factorial divided by 5 to the n. So what do we want to do? We want to find the Taylor series for f about x equals 2. All right, so if you remember the general formula for a Taylor series centered at x equals a, or in this case x equals 2, I guess, we can write f of x as sigma sum n equals 0 to infinity of the nth derivative evaluated at the center point, which in this case is 2, divided by n factorial times x minus 2 quantity to the n. All right, so again, we need to find an expression for the nth derivative of f at 2, and this is what I meant by the problem giving us a head start. It just told us what it is by magic. So all we need to do then is just plug it in for that expression and see what we get. Sigma sum n equals 0 to infinity of 2 to the n times n plus 3 times n factorial divided by 5 to the n. So that's this formula right here, but in context, it is divided by an additional factor of n factorial, so be careful not to forget that. So that's there, and then we have x minus 2 to the n. All right, and so simplifying this a bit, we have that the two n factorials cancel away. And so we're left with sigma sum of 2 to the n times n plus 3 over 5 to the n times x minus, whoops, not 3, x minus 2 to the power n. There we go. All right, very good. All right, so let's go on to example 4. So example 4. All right, so the task here is we want to find the Taylor series for this function, f of x equals 1 over 3x plus 1, but we want it centered at x equals 3. And we also want to know what the radius of convergence is. All right, well, we could tackle this using the general method again if we wanted to. Based on my tone, you probably can guess that that is not what I want to do. And can you blame me? What is it going to involve? It's going to involve taking lots of derivatives of this thing, which is going to be, I guess, well, it's going to be a power rule thing, but it's going to have a chain rule attached to it. So we're going to get factors of 3 popping out, but then we're also going to have to deal with negative exponents. And anyway, it sounds kind of like a mess. However, this formula looks, again, awful familiar in structure, right? It looks kind of like the 1 over 1 minus x function, or the a over 1 minus r expression, for which we know immediately how to write a series expression. So indeed, if you're like me, your mind may have already jumped straight over to that, and in a hurry, you might have gone ahead and basically solved this problem, or seemingly so, by saying, aha, a over 1 minus r, this matches up with that perfectly. I just have to remember there's a double negative there. So this becomes sigma sum n equals 0 to infinity of negative 3x to the n, And so then I'm done. Except that I'm not. So the issue is I'm forgetting again about the center point. So yes, this is true. This works. But the issue is this is a Taylor series centered at x equals 0 again, because we have just x to the power n if I was to expand it out. But what I want is a power series expression where I have x minus 3 raised to powers of n, not x to the power n. So then the question again comes up, well, how do I go and make that appear? Or, I guess, to be a little more precise, how can I get this in a series expression involving x minus 3 to appear while still somehow piggybacking on the known series formulas for 1 over 1 minus x or for a over 1 minus r? Well, as you might be able to guess, I'm going to make use of the standard mathematician's trick again of making what I want to appear just appear as if by magic, and worry about the repercussions for that later on. See, so this is a proof for why mathematicians are the most rash people in the world. They just go and do stuff and worry about the consequences later and clean up the mess afterward. Although arguably certain engineers are like that too. Okay, anyway, before I go and cause a riot, let's go ahead and try to solve this. So, okay, so here's my idea. So we're starting with 1 over 1 plus 3x. And so my idea is I don't like the fact that that's just an x by itself. I want it to be an x minus 3. So let me just, by magic, make it appear. So I'm just going to plug in x minus 3 in for x. There's what I wanted. Although I'm not allowed to just do that for free, so I think in this case I'm going to be a bit of a good boy and clean up my mess before it becomes a mess. So I'm not allowed to just magically subtract 3 from x. So what I'm going to do is I'm going to undo that by doing a plus 3 over here. So everything's okay now, but I've written this out so that an x minus 3 at least shows up somewhere in the expression. And now that it is showing up in the expression, I'm going to be very, very reluctant to let it ever disappear again. So what I'm going to do now is I'm going to distribute this 3 through, but I'm going to treat x minus 3 as a block. I'm not going to distribute to both of these terms. I'm going to treat x minus 3 as if it's a block and distribute the 3 to the block x minus 3 by itself, and then distribute it to this other 3. So what I mean by that is I'm going to get 1 divided by 1 plus 3 times the entire block x minus 3, which I don't want to go away, and then plus 3 times 3, which is 9. All right, and so combine the 1 and the 9 like terms, and I'm going to get 10 plus 3 times x minus 3. All right, so now I finally have an x minus 3 showing up, and this is completely clean because I undid it by having a plus 3, so I already cleaned up my mess. So now I just need to find a way to make use of this formula, a over 1 minus r, to turn it into a series. Well, it already looks a little bit like that, but we're not quite there yet because I have a 10 in place of a 1, but it's not hard to make a 1 show up. I just divide both numerator and denominator by 10. So if I do that, numerator becomes 1 over 10, and denominator becomes 1 plus 3 times x minus 3, all divided by 10. All right, and now this is matching up very well with a over 1 minus r. So now let's turn it into the series expression. So how does this work? So I get the a factor just popping up in there. So I have 1/10, just all by itself, and then times r to the power n. And in this case, remember the negative sign. This is a plus, that's a minus. So I need to take the negative of this when I plug it in over here. So I'm going to have negative 3 times x minus 3 over 10, that to the nth power. All right, well, this is already looking quite a bit more promising because now I have my x minus 3 there. But let's see if we can clean this up a little bit so it looks more like a standard Taylor series where we have coefficient times x minus 3 to the n. Okay, so that shouldn't be too hard to do. So first of all, I'll go and distribute the n to every factor in there. So the 1/10 is just going to hang on for now. And I'm going to get a minus 1 to the n to start off, distributing it to the negative sign, times 3 to the n times x minus 3 to the n divided by 10 to the n. And if I go and multiply the 1 over 10 through, I'm going to have, I think, minus 1 to the n times 3 to the n. I think I'm going to separate the x minus 3 apart. And down below, I'm just going to have 10 to the n plus 1 times x minus 3 to the n. All right, and I think we have accomplished our mission. Centered at 3, as required. All right, and so now for part 2 of the question. Let's not congratulate ourselves too hard yet. We need to find the radius of convergence. Well, okay, so that's not too hard to do. We made use of the geometric sum formula, so we already know how to find the radius in that situation. Excuse me. All right, so we just need to find out what this little r was in terms of x. So what expression was playing the role of little r? So it was this one right here, I think, right? Except it has a negative sign in front of it. So the condition for convergence is the absolute value of r needs to be strictly less than 1. So in this case, that means the absolute value of negative 3 times x minus 3 over 10 needs to be less than 1. So in this case, absolute value is going to kill the negative and multiply and divide by 10 and 3. We're going to get the absolute value of x minus 3 is less than 10/3. And actually, we can stop here if we wanted to. This is actually going to be our radius. But since I haven't ever done that before, let me go ahead and show why. So we'll go ahead and solve this out for the entire radius of convergence. So to undo an absolute value being less than something, we go and drop the absolute value bars in exchange for turning this into two inequalities. X minus 3 is less than 10 to the third, or 10 over 3 rather, and greater than negative 10 over 3. All right, and then I add 3 to both sides, and I get that x has to be strictly in between 10 over 3 plus 3 and, I guess, negative 10 over 3 plus 3. All right, and the radius of convergence is just going to be the length of this interval. So the interval from this left endpoint to that right endpoint divided by 2. And I think you can already see what's going to happen over here if I subtract this from that, or rather if I subtract this from that, get the order of subtraction right, then the 3's are going to cancel, and I'm going to get 10 over 3 minus a negative 10 over 3. So I'm going to wind up having 2 copies of 10 over 3. But the radius, but to get the radius, I divide by 2. So really, this is just 2 times 10 over 3, and then I divide by 2. So really, I just get 10 over 3. So indeed, the radius of convergence is going to be 10 over 3. Matching up with that. The other way you can think about it too, if you didn't like this method, the other way you can interpret what this is saying is absolute value of x minus 3. Think about kind of what the meaning of absolute value of something minus something means. It means the distance between x and the number 3 is less than 10 over 3. So I'm saying over here, this expression is saying geometrically, more or less, that on the number line, x can be no further away from 3 than 10 over 3. The furthest distance in either direction that x can wander away from 3 is 10/3 units away from 3. So in other words, that's a radius. It's the length of the leash that x is attached by. All right, so let's do a similar example, or an example in a similar vein, except we'll throw in one extra complication into the mix. All right, so example 5, find the Taylor series for f of x equals ln of x centered at x equals 5. All right, so again, we could do this with the general method if we wanted to. In this case, it wouldn't be, I guess, quite as painful. The derivative sequence would be 1 over x, and then I think negative 1 over x squared, and then I think you get a negative 2 popping. Well, okay, so fine. There's still a little bit of pain in there, but I guess it wouldn't be that bad. But as usual, I would prefer to go to a lot of work to avoid going to a lot of work. So is there any way that, again, I can piggyback on any known series in order to get this expression for free without having to go and compute like 7 derivatives? Well, I think maybe. So, I mean, as far as ln of x goes, we don't have any series formulas for just ln of x. Pretty much nothing. But if I take one derivative of f prime of x, I get 1 over x. And that, in some very vague capacity, looks a bit like 1 over 1 minus x, for which we do have a series expansion for. So is there any way for me to make it look like this, or the more general version, a over 1 minus r? Because it already kind of has that structure, but it's not really there yet. We don't have a 1 minus, it's just an x all by itself. But nevertheless, it's close enough that it might be worth trying to figure it out. So any ideas, you guys? By that, I mean you should pause the video and come up with some ideas. Come on. Okay, fine. All right, so, well, okay, so let's think about what it is that we want. So we want a Taylor series that is centered at x equals 5. So what that means is we want to get a power series expression involving this factor, x minus 5. This is what we want to show up in any formula that we're going to convert into a series. So at the moment, we just have x. Can we convert that into an x minus 5? Of course we can. We can do anything, as long as you remember to clean up the mess later. So, all right, so that's what I'll do. Let me just turn x into x minus 5. But I need to clean up that mess, so I'll clean up that mess right now. I'll put a plus 5 right there. All right, and now that I have my x minus 5, I'm going to guard it with my life and not allow it to cancel with anything ever again. So I'm just going to move the 5 around then. So I'm going to have 1 divided by 5 plus x minus 5. All right, so we're pretty close to this form, but not quite, so we need the 5 to become a 1, but we already know how to do that, right? We just divide numerator and denominator by 5. So if I do that, I'm going to get 1/5 on top, and on bottom we're going to have 1 plus x minus 5 over 5. All right, and now this is lining up quite nicely with a over 1 minus r. All right, so let's turn it into its series form then. Sigma sum n equals 0 to infinity of 1/5 times x minus 5 over 5, that thing to the nth power. All right, and if I simplify it a little bit to make it look more power series-esque, I'm going to get x minus 5 to the n divided by 5 to the n, and combine those. We get x minus 5 to the power n divided by 5 to the n plus 1. All right, so mission accomplished. Almost. So we did quite a bit of work there, so much so that you are tempted to think that we must be done with the problem because we already suffered so much. But remember, all that we really did was we found the Taylor series expansion centered where we want it to be at x equals 5, but not for f of x equals ln of x, but for f prime of x equals 1 over x. So as a reminder, all that we've really done here is we found a nice Taylor series expansion for 1 over x, but we need it for ln of x. But if you remember from what we were doing with power series last time, we know how to get an ln of x to appear here. We will just integrate both sides. If we have a Taylor series representation for f prime, we can get one for f by integrating everything. So in that case, f of x is going to be the integral of this thing. So, all right, I'll go ahead and write it out. So integral of this entire series. And again, integration is nice. It plays very nicely with addition. So to integrate this, I just integrate each term independently. But I have to remember to add a plus c. So I'm going to write the plus c at the beginning. So, or c plus rather. So c plus the sigma sum of the integral of this thing with respect to x. So remember, we're integrating now. So in that case, x is the variable and n is the constant. So, so what's the rule? So the exponent goes up by 1, and then I divide by the new exponent. So I get sigma sum of x minus 5 to the n plus 1 divided by 5 to the n plus 1 times n plus 1 on bottom. All right, but then again, remember, we're still not done because c is a constant we need to actually solve for. We can't just leave an arbitrary constant there because f is not arbitrary. F is definite. F is ln of x definitely. So we need to find out what c actually is in this case. And so the way we do that is we plug in the center point. So in this case, the center point is 5. So plug in 5 in for x. And what happens over here? Well, I'm going to have c, and then if I plug in 5, well, what's going to happen? I'm going to have 5 minus 5, which will cause everything in here to cancel out, it looks like. All right, so just to be sure about it, I'm going to have sigma sum of 0 to the n plus 1 over 5 to the n plus 1 times n plus 1. And yep, 0 raised to any power, or any non-zero power, is always going to be 0. And in this case, we're good to go because we have n plus 1. We're starting at n equals 0, but we're raising it to n plus 1. So indeed, this is well defined. We get that we're just adding up a bunch of zeros. So this thing is just going to be c. But we know from the original definition of f that f of 5 has to be ln of 5. All right, so evidently, c is ln of 5. So we get our final answer then, our final Taylor series, is going to be ln of 5 plus the sigma sum from n equals 0 to infinity of x minus 5 to the n plus 1 over 5 to the n plus 1 times n plus 1. And now we are done. Right? Well, yeah, I mean, we're done here. Although there is actually one optional thing you can do if you want to clean this up and make it look a little nicer. So if you notice, we have a bunch of n plus 1s sitting all over the place, which is fine, but it's kind of a clunky bit of notation. We would like it if it was just, say, x minus 5 to the n, 5 to the n, and just n on bottom. Fortunately, we can convert it into that. I mean, think about what's going on here. We have a sigma sum, and we're starting at n equals 0. And so if I plug in n equals 0, I'm really just going to get, as my first exponent, I'm just going to have 1, and then down here I'm also going to have 1. So really, this n plus 1 showing up here in a sigma sum that is starting from n equals 0 is really trying to tell us that, hey, this is a sigma sum that really ought to start at n equals 1. N equals 0 is kind of artificial, and we're having to adjust for that inside the series by having all these plus 1s everywhere. So really, you could clean this up a little bit if you re-index this to start at n equals 1 instead. If I start this at n equals 1, then I don't need this extra adjustment of plus 1 to show up anymore. So then we have just x minus 5 to the n divided by 5 to the n times n. Whoop, there we go. Okay, now for a bit of a break. So this example is kind of similar to example 3, although it's kind of a backward example from example 3 in a bit. So if you remember, example 3, we were given what the nth derivative of f at a certain point was, and we wanted to derive a Taylor series. So in this case, we're going the other way around. We have a Taylor series, and we want to find the nth derivative, or really just the 10th derivative in this case, evaluated at 7. All right, so what's the setup here? So we have a Taylor series for some function f of x centered about x equals 7, and here it is. Here's the Taylor series. And so the question is, all right, based on this knowledge, what is the 10th derivative of f evaluated at 7? All right, so to get a handle on this, let me real quick go ahead and write out what the generic formula for a Taylor series is, centered at x equals 7. So it's sigma sum, n equals 0 to infinity, of the nth derivative of f at 7 divided by n factorial times x minus 7 to the n. And in this case, we are told that this series is 3 to the n times n plus 4 divided by n plus 1 factorial times x minus 7 to the n. All right, so what we want is, well, ultimately we want the 10th derivative of f, but we can find that if we know what the nth derivative of f is at 7. So how can we find that? So you might already kind of see a way to do that. So it turns out that power series, just like, or Taylor series, just like polynomials, they are uniquely determined by their coefficients. So in this case, by coefficients, I mean these things. These are the coefficients of my Taylor series. And so it turns out that, just like with polynomials, if you have a Taylor series equal to a Taylor series, and they are supposed to be equal to each other for all values of x where they converge, then just like with polynomials, if you're in that situation with polynomials, remember partial fractions, that allows us to say, all right, then the coefficients must be the same in both polynomials or in both series. So that's what we can say here. Because these two series are supposed to agree for all values of x that are possible, that must mean that these two coefficients are actually equal to each other. All right, so we can derive then this equation. We have the nth derivative of f at 7 divided by n factorial must be equal to 3 to the n times n plus 4 divided by n plus 1 factorial. And from here, we can just solve for the nth derivative of f. So it looks like there's mainly just one thing to do. I just need to multiply both sides by n factorial. So we'll go ahead and do that. We get 3 to the n times n plus 4 times n factorial divided by n plus 1 factorial. And just like before, n plus 1 factorial can be turned into n plus 1 times n factorial, which will then happily cancel with the 1 that appears above. And so we get the nth derivative at 7 is 3 to the n times n plus 4 divided by n plus 1. All right, and so we're interested in the 10th derivative. So the only thing we need to do then is plug in 10 for n. 10 for n. I think the quarantine is getting to me. All right, so the 10th derivative of f at 7 is going to be 3 to the 10 times 10 plus 4, that is 14, divided by 10 plus 1, which is 11. There we go. All right, so I have one last example for you, and we're bringing it full circle. It's like example 1. So let's see if we can find the Taylor series expansion for cosine of x, centered at good old x equals 0, and find its radius of convergence. All right, well, okay, so this is cosine of x. I don't think there's any really easy way to go and find the Taylor series with any other series we've got so far, right? So I think we're just going to have to fall back on the general formula for a Taylor series, or a Maclaurin series, I guess you could say in this case. So what does it say? We have f of x is equal to sigma sum n equals 0 to infinity of the nth derivative of f at 0, hope that's legible, divided by n factorial times x to the n. All right, and the task is we need to find out what this factor is. All right, well, I think we know a procedure for that. So I don't think we have any better course in this case than to just take a bunch of derivatives of cosine. But that's not too bad. It's just going to be it's just going to alternate between cosine and sine with some -1 sine flipping along the way. But on the whole of it, not so bad. So let's start off. So we have the 0th derivative is the original cosine of x. The first derivative is going to be negative sine x. Second derivative is going to be negative cosine x. Third derivative is going to be positive sine of x. And fourth derivative, we've gone full circle, we're back to cosine. All right, so that's probably enough. All right, so let's plug in 0 into each of these and see what we get, if we can identify a pattern going on. All right, so f of 0, that's cosine of 0, which is just 1. F prime of 0, that is going to be negative sine of 0, but sine of 0 is 0, so this is just going to be 0. Next up, we have minus cosine x, so f double prime at 0. We're going to have negative cosine of 0, so that's going to be a -1. And over here, we're going to have sine of 0 for my third derivative of f, so that's just going to be sine of 0, that's 0. And the fourth derivative, well, we've just gone full circle, so this is just going to be back to being +1 again. All right, so I think you can see a pattern here, right? It's a fairly simple pattern as far as it goes, or at least it's easy to describe, to understand. It looks like we are going to be alternating between plus and -1 all the way down, but every other term is just going to be a 0. So if I was to continue this pattern, we would have a 0, and then a -1, and then another 0, and then a 1, and then so on and so forth. But then the question is, well, how on earth do I encapsulate this this pattern, simple as it might be, as a formula? It's not really clear how you do that. Well, so in that case, let's not do that for now. Let's go and write out a few concrete terms of what this series looks like and see if we get a better idea that way. All right, so I'm just going to go up here. So let's write out a few terms. So let's start off with n equals 0. So n equals 0, that corresponds to this coefficient right here. So we're just going to have 1 divided by 0 factorial, which is also 1. So this entire coefficient is just going to be 1. And we'll have, this is the constant term, right? Because n is 0, and x to the 0 power is 1. So evidently, the initial term is just 1. All right, so what's the next term? If I plug in n equals 1, then I'm going to get f prime of 0 is 0, which is just going to annihilate everything. So I don't actually have a linear term in this case, so we'll just skip it. So this one is just going to be skipped. Let's say ignore. All right, so n equals 2. We're going to have a negative 1 on top, so I'm going to write that as a minus right here. And we're going to divide by 2 factorial. So it looks like I'm going to have negative 1 on top divided by 2 factorial times x squared. All right, if I plug in n equals 3, then the coefficient is going to be 0 again. So I can just skip it, another ignore. And after that, I have the fourth derivative, in which case I'll be back to a 1 on top, but on bottom, n factorial for n equals 4 is going to be, well, 4 factorial, whatever that is, times x to the fourth. And I think you can see what the pattern is, right? So there's no odd terms. Every odd term is skipped. And we're alternating, so we have 1 minus and then a plus. And so the next one, you might be able to guess, is going to be 1 over 6 factorial times x to the sixth, and so on. All right, so the question is, can we go and, does this help at all? Can we go and write this out as a formula any more easily? I think actually yes, though it may not be clear yet. So let me go and clean it up slightly. I'm tired of looking at all these fractions. All right, so I'm going to free up this space down here. And let me copy this again. All right, so we have f of x is equal to 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial, and so on. I think the pattern is pretty clear. The question is, can we write this as a sigma sum formula? So I think we can for a little. So, well, okay, so let's just go one piece at a time. So let's start off with sigma sum from n equals 0 to infinity. The first thing, the most basic thing I note about this series is it's an alternating series. We have +1, we have a plus and then a minus, a plus and then a minus, and then a plus and then a minus, and we're starting with a plus term. So what that tells me is we should have a negative 1 to the n no matter what. And what's next? Well, the thing is, I'm going to be skipping all of the odd terms. So I only have even numbered numbers that are showing up in each term. So every term that I go up, I just get the next even number. Over here, I had basically zeros, x to the 0 over 0 factorial, which is invisibly just a 1. And over here, we have the next even number, 2, and then the next even number, 4, the next even number, 6, and then so on. So what I think I'm going to do here is, instead of letting n represent every possible power of x, even the ones for the coefficients which are 0, let's let n represent the nth even number. So n, this n, is still going to be, is still going to go run the usual course. It's going to go from n equals 0, and then n equals 1, and then n equals 2, and n equals 3. We're not going to skip the odds here, but we will go and let it represent which even number in the sequence we're dealing with. So 0 is the 0th even number, 2 is the first even number, 4 is the second even number, and 6 is the third even number. And so I think you know how to go and convert that into the actual number. The nth even number is 2n. So I can write this out as x to the 2n divided by 2n factorial. And if I'm not mistaken, I think that does it for us, right? So let's test out a few values. If I plug in 0, negative 1 to the 0, then that's positive, it goes away. Then I have x to the 0 over 0 factorial. That gives me a 1, so far so good. Plug in n equals 1, I get a negative, which I do, which I'm supposed to. And if I plug in n equals 1 here, I get x squared over 2 factorial, which is exactly what I wanted. And if I plug in n equals 2, negative 1 squared is back to being positive 1. And we have x to the 2 times 2, which is 4, over 4 factorial, 2 times 2. So yes, I think we have succeeded. There is our Maclaurin expansion for cosine of x. All right, so the only thing left to do then is to find the radius of convergence. So I think we can do that just using the familiar old ratio test. Now that we have this in hand, let's go and try it out. So we'll have the ratio of a sub n plus 1 over a sub n in absolute values. So let's compute what that's going to be. So that is absolute value of -1 to the n plus 1 times x to the, so I think I'm going to get, if I simplify it, a 2n plus 2. And down below, I'm going to have 2n plus 2 factorial. And then times the reciprocal of the original. So that'll be a 2n factorial on top. And on bottom, we'll have -1 to the n times x to the 2n. All right, so let's see what cancels with what. X to the 2n is going to cancel with all but 2 copies of x in the numerator. So we have just an x squared remaining. We have -1 to the n. It's going to partially cancel with that. But really, I don't even need to think about that at all, because this entire thing is enclosed in absolute values. So it doesn't matter what, whether this is a plus or a -1, the absolute value is just going to make them all positive. So I can just cancel everything completely thanks to the absolute value. And then I have to deal with this, the factorial cancellation. So this one has to be done a little more delicately, because this is not 2n versus 2n plus 1. This is 2n factorial versus 2n plus 2 factorial. So let me not do anything too hasty. So let me go ahead and see what we have left over after the cancellations we've gotten so far. So I think what we're left with is x squared times 2n factorial over 2n plus 2 factorial. All right, so how do I cancel 2n plus 2 with 2n factorial? I think this one is clearly the bigger product, right? This is multiplying all of the integers from 1 up to 2n plus 2 together, which is more integers being multiplied than just this one. So let me go and expand this one out a little bit. All right, so I can break this apart into 2n plus 2 times 2n plus 1 factorial if I wanted. But that doesn't help really. I still can't cancel anything, so maybe I'll go one more down. So this factorial can break apart into 2n plus 1 times 2n factorial. I think now we're in business. Now we can cancel these out. All right, so evidently all we're left with is x squared on top over 2n plus 2 times 2n plus 1. And actually, I don't think I even need the absolute value bars anymore, right? Because x squared is always positive, and these guys are definitely going to be positive as n goes to infinity. So I can just drop the absolute value bars completely. All right, and so now we'll take the limit as n goes to infinity, which means, again, that x is held fixed as a constant. So if n goes to infinity, this is a constant divided by a quadratic. And in that case, that is very much a bottom-heavy rational function. So if you take n to infinity, you are going to get 0. And again, that works for all values of x. It doesn't matter what x you pick, you will always get 0, no matter how big x is, because if it's fixed, if it's a constant, it's eventually going to be dominated by this quadratic that is downstairs. So indeed, we get it converges to 0, which tells us by the ratio test that this Taylor series, or power series rather, any series, the ratio test doesn't care, it converges for all x values. Which tells us then that our radius of convergence is infinite. All real numbers work. There you go.
All right, one last thing. I've shown you now the general method by which you construct a Taylor series, but I don't want you to forget about the method using the geometric sum formula, because its great advantage is that when it works, it is a much quicker way to derive a Taylor series than the general method. But it's not the only shortcut we can use to derive Taylor series. We have already derived the Taylor series formulas for e to the x and cosine of x, but there are several other important fundamental Taylor series. These include the Taylor series expansions for sine of x and arctan of x. Just like with the geometric sum formula, these fundamental Taylor series can dramatically speed up the process by which we derive Taylor series for composite functions. And next video, we'll tackle how this is done. In the meantime, please work on getting these Taylor series memorized. You will not be provided them on an exam, and you don't want to have to derive them from scratch when the clock is ticking. Now, I personally am not a big fan of memorization, but actually, I don't think these series are too hard to memorize if you approach them in the right way. Don't try to memorize the series formulas. You'll just get lost in the symbols. Instead, write out the first 3 or 4 terms of each series and take note of the patterns you see emerge. It's much easier to memorize a pattern than to memorize a splattering of symbols.